everyone. Let's look at radical expressions in rational exponents. This is in chapter 8-6 of your textbook, which you can check out these same examples, but I'm going to work through these so that way you can get a better understanding. So, if you see on the left-hand side of the screen right here, I've got the square root of 25. We know that the square root of 25 is 5. It could also be negative 5, right? Because if we were to square this, if we squared positive 5 we would get 25, and if we squared negative 5 we would get 25, so either way we would get 25. Okay, so now let's look at the cube root. So to figure out what the cube root of 8 is, I have to figure out what number multiplied by itself a total of 3 times will give me 8. Well, 2 cubed will give me 8. So the cube root of 8 is 2. The cube root of negative 8, we can take the cube root of a negative number, because what negative number multiplied by itself 3 times will give me negative 8? Well, negative 2 cubed will give me negative 8. Negative 2 times negative 2 is positive 4, but times negative 2 again is negative 8. So the cube root of negative 8 is negative 2. And similarly, the fourth root of 16, what number multiplied by itself 4 times is 16? Well, I can have positive 2 or negative 2, because no matter which one I use to the fourth power, I will get 16. So, generally speaking, the nth root of b is equal to a if a to the n power equals b. So this n is what we're going to call the index, plural indices. The b is the radicand. So when we're looking at the definitions or the generalizations of properties of these roots, the index and the radicand are referred to as such. Okay, so let's check out this table, which is on page 610 of your book. So if we have an odd index, that little number that's in front of the radical sign, so if it's odd, then there will be one real root. For example, the third root of 8 is 2, as seen over here. So the cube root of 8, or the third root of 8, is equal to 2, and there was only one root for that. If the index is even and the radicand is positive, then we'll have 2 real roots, one of them positive and one of them negative. For example, the fourth root of 16 is positive and negative 2, because either one to the fourth power will give me 16. If we have an index that is even and a negative radicand, for example, anytime we took the square root of a negative number, well, there are no real roots. So anytime that number is even, the index is even, then there are no real roots. For example, the fourth root of negative 16 has no real roots, no real fourth roots. And then if the radicand is 0, then there is one root, and it is 0. So the third root of 0 is 0, the fourth root of 0 is 0, and so on. So let's look at some properties of nth roots. And for both of these, this is when the index and the radicand are greater than 0. So we have the product property of roots. So if we have the cube root of 16, then we can split that into 2 separate cube roots, just like we did with square roots before. So the cube root of 8 times the cube root of 2. 8 times 2 is 16. So we can split them into separate radicals. So then the cube root of 8 is 2, and then we cannot evaluate the cube root of 2, as simplified as that gets. We'll have 2 cube roots of 2. So in general, if we have the cube root of a times b, we can split that into the cube root of a times the cube root of b, which can be helpful when we're simplifying things in a few examples. Just like with multiplying, we can also do this when we're dividing. The quotient property of roots, the nth root of a quotient is equal to the quotient of the nth roots. So if we have this square root of 25 divided by 16, we can split that into the square root of 25 divided by the square root of 16. And the square root of 25 is 5, and the square root of 16 is 4, so that would be simplified to 5 over 4. So in general, the nth root of a divided by b is equal to the nth root of a divided by the nth root of b. So knowing these properties, let's look at a couple of examples here. We have the cube root of 27 times x to the 6th. So let's use the product property here. So we have the cube root of 27 times the cube root of x to the 6th. So the cube root of 27 is 3 because 3 times 3 times 3 is 27. And the cube root of x to the 6th, well, we have to figure out what times what gives me x to the 6th. So that's actually x squared. X squared times x squared times x squared is x to the 6th. So the cube root of x to the 6th is just x squared. So the cube root of 27x to the 6th is 3x squared. On the next example, we have the cube root of x cubed divided by 7. So let's go ahead and split that into two separate radicals. So we have the cube root of x cubed divided by the cube root of 7. Well, the cube root of x cubed, easy enough, that's x. So we'll have the x divided by the cube root of 7. But we don't want to leave the cube root of 7 in the denominator. We want to rationalize the denominator. So here's the thing with these. Whenever we were rationalizing denominators that had square roots in them, we only had to multiply by itself to get rid of the radical. But here, we actually have to multiply it, a total of 3 times. So we'll have the cube root of 7. So this is multiplying it by 1 the first time, because the cube root of 7 divided by the cube root of 7 is equal just to 1. But we actually need to multiply it again by a version of 1. Because in our denominator here, we'll have the cube root of 7 times the cube root of 7 times the cube root of 7, which is the cube root of 7 times 7 times 7. And then up here, we'll have the x times the cube root of 7 times 7, which is 49. The cube root of 7 times 7 times 7 is just 7. So we have x cube root of 49 divided by 7, and that's your answer. So whatever your index is, that tells you how many times you should be multiplying that denominator by itself. Okay, now let's look at some rational exponents. A rational exponent is an exponent that can be expressed as m divided by n, where m and n are integers and n is not equal to 0. Radical expressions can be written by using rational exponents. So what we did a second ago, we can rewrite that as a rational exponent, and let's look at how. So for any natural number n and integer m, the exponent 1 over n indicates the nth root. So for example, if we have 16 to the 1 over 4 power, that means that we can rewrite this as a radical as the 4th root of 16. And then we can evaluate that to be equal to 2. So in general, a to the 1 over n power is equal to the nth root of a. So if that numerator is not equal to 1 as seen as in that first line, if it's equal to m, then that means it's still the nth root, the number on the bottom, but it's raised to the mth power. They chose 2 letters that are really hard to say. Okay. So a to the 2/3 power means the index is 3, the number on the bottom is the index. So the cube root of 8, and then the number on the top tells us that we're then going to square it. So the cube root of 8 is 2, then we'll square it so that it's 4. So just so you know, you can rearrange it. You could also have the cube root of 8 squared. The 2 can go inside the square root or the radical or outside the radical. It doesn't matter. You'll choose the one that is easier, makes it easier to simplify. You'll see in just 1 second. So let's write the expression negative 125 to the 2/3 power in radical form and simplify. So there's 2 different methods that we can do this. First one is to evaluate the root first, and then the other one is to evaluate the power first. So let's see what that means. So one way that we could write this 2/3, is in parentheses, we have the cube root. Our index is always the bottom number, the cube root of negative 125, and then square it. The power is the numerator. So we can do it this way. Sorry, there's so many bells. Okay, the cube root of negative 125, what times what times what gives me negative 125? Well, that's negative 5. And remember, we can take the cube root of a negative number. So if the cube root of negative 125 is negative 5, then we square it. Negative 5 squared is 25. So that's one way you could do it. Or, instead of having the squared on the outside, we could put the square on the inside. So we would have the cube root of negative 125 squared. Negative 125 squared is 15,625. And then what times what times what gives me 15,625? And that is 25. So you can see it doesn't matter which way you do it. It might be easier one way versus another, but you'll get the same answer in the end. I would probably, for this example, have chosen the one on the left because it dealt with smaller numbers, but even if you chose to go with the method 2 here, it still works. Let's practice writing expressions by using rational exponents. So in example A here, we have the 4th root of 7 cubed. So our base here is 7. So then our exponent, the index is 4, so that goes on the bottom. And the power is 3, so that goes on the top. So 7 to the 3/4 power. That's how we can rewrite that expression as a rational exponent. So again, let's look at example B here. We have the cube root of 11 to the 6th power. So we have 11 is our base right there. The index is 3, so that goes on the bottom of the rational exponent, our denominator. And then the numerator is our power, so 6 divided by 3. Well, 6 divided by 3 is 2. So really we have 11 squared here. And 11 squared is equal to 121. So in this case, we would simplify it all the way down to 121 because we can't always simplify as much as possible. Okay, and finally, let's talk about one more thing. Here you see a table of properties of rational exponents. So we have the product of powers property, which is whenever we are multiplying like bases, like 12 and 12, then we will add together the exponents to simplify. So 12 to the 1/2 times 12 to the 3/2 is the same thing as 12 to the 1/2 plus 3/2. Well, 1/2 plus 3/2 is 4/2, which is equal to 2. So 12 squared is 144. The quotient of powers property is the same way, except when we are dividing like bases, instead of adding them, we'll subtract them. So 25 to the 2/3 divided by 25 to the 1/3 is equal to 25 to the power of 2/3 minus 1/3. Well, 2/3 minus 1/3 is just 1/3. And 25 to the 1/3 power, the cube root, remember it's the same thing as the cube root of 125, is equal to 5. If we have a power of a power, we multiply them. So 8 to the 2/3 power raised to the power of 3, raised to another power, then you'll multiply those exponents together. So 2/3 times 3 is just 2, so 8 squared is 64. We also have power of a product property. To find the power of a product, distribute the exponent. So if we have 16 times 25 raised to the 1/2 power, then we can distribute the exponent to each of them and have it 16 to the 1/2 times 25 to the 1/2 and simplify it from there. This is really similar to taking a square root and splitting it into 2 square roots. I mean, it's really the same thing. This time we're just using rational exponents. And then we can also do the same thing when we're dividing, so the power of a quotient property. So if we have a fraction raised to, for 16 over 81, raised, for example, to the 1/4 power, then we can split that into the 16th to the 1/4 power divided by 81 to the 1/4 power, which is just like taking a fourth root and splitting it into 2 separate radicals to evaluate, which here this simplifies to 2/3. So let's look at these two examples over here. So we have 25 to the 3/5 power times 25 to the 2/5 power. So to simplify these, always think about which property you can use. Well, I have like bases here. They're being multiplied. So when I have like bases and it's being multiplied, I add the exponents together. So I have 25 to the 3/5 plus 2/5, and that is equal to 25 to the 3/5 plus 2/5 is 5/5. Well, 5/5 is just 1. So 25 to the 5/5 power is 25. And then if, for example, B, if we're dividing, here we have like bases. So when we're dividing like bases, you subtract the exponents. So we'll have 8 to the 1/3 minus 2/3. That is equal to 8 to the negative 1/3. And we have something here called the negative exponent property. Whenever you have a negative exponent and you want to make it positive, flip it from the numerator to the denominator or vice versa. So for here, we'll do, this will turn into 1 over 8 to the positive 1/3 power. So again, let me just jot that down so you can see exactly what I'm saying. This is called the negative exponent property. So if it's in the numerator and it's negative, just flip it underneath the fraction. So we'll have 1 over 8 to the 1/3. It's just the reciprocal. And then 8 to the 1/3 power. So what is the cube root of 8? It's 2. So what we have here is 1 over 2. So in the end, that's what that would simplify into. Okay, so that's it. I hope that was clear enough. If you have any questions, let me know. And again, you can check this out in your textbook, Chapter 8, Section 6, Radical Expressions and Radical Exponents. And I will see you later. Bye.